Hi everybody. So we're going to do one more practice problem. We're going to be talking about the hydrostatic pressure on a dam. So I'm going to be drawing the dam here. Dams are pretty common. We use them to store water behind them and to run pumps and mills that generate energy. And so having a dam that doesn't break because of the water pressure exerted on it from behind is probably a generally good idea. And so we need to, in order to design that, you need to know what the water pressure exerted on it is. Now, the difference between this and the cube earlier is that we don't have a top side and a bottom side to worry about. Instead, we just have a single flat face. So this is the front-facing view side of it, and on the side view, you have something like this, where the water is over here, right? And here's the dam. So the water level is on this level on the front-facing side. Let's say that the dam is 20 meters tall. And let's say the water level goes up 16 meters. Now, let's say also that the dam on the whole is 50 meters wide at the top, 50 meters wide at the top, and 30 meters wide at the bottom. You can split up this dam into several shapes. You can split it up into one general rectangle here that's 30 meters wide, and then two right-hand triangles, right? And that's going to be useful because part of the challenge of this is actually just the geometries. As we've already gone over the calculus and some of the simple algebra that's involved in hydrostatic pressure, you should find that easy at this point, and we'll just have to worry about some of the odd geometries. And this is about as odd as it gets for our practice problems. So we can divide this section, for example, the section that I'm outlining in red, this right triangle, into that right triangle, which I'm going to show here, and a similar right triangle, which I'm going to outline in dotted green, that's inside of it. We're going to define a certain variable called A. The variable A is going to be the length of this portion, essentially. And the reason why we want to define it is this variable is dependent on the depth at which we're talking about this dam, right? So we're also going to define the variable xi. Xi is the depth, as we're talking about, the depth underneath the water that we're talking about this given section, this given slice of the dam at which we're going to find a pressure. And as we went over earlier, the width of this slice, or the height of this slice, is, we're going to call it delta x, but it's infinitesimally small. Essentially, we're going to have an infinite number of these slices, and so we don't really have to worry about delta x terribly much. What's more important is xi. So as we know, there's no water or hydrostatic pressure above this point in the dam from here to here, and so we're only going to be concerned with the 16 meters that's covered by water underneath. Now, when we divide this section to xi and the 16, you can essentially count, we're going to try to qualify some of the sides of this triangle here. Now, we know that this is 50 meters. This dam is 50 meters long. So we know that this section, this little square, is actually 30 meters, which leaves 10 meters on each side for these triangles, which means this side of the triangle is 10 meters. We know that this dam is 16 or is 20 meters tall, and we know that this A has to be, the side of this A is essentially 16 minus xi. The greatest that this A value could be is 16 because that's the water level, that's the highest water level, and we're subtracting xi because that's the depth at which we're taking this measurement of the pressure along this line. And so this is important for qualifying the depth. So once again, the depth is 16 minus xi. Now we also need to know the width of this slice, right? So the width is this span along the slice, and we're going to call that W. Now W is equal to 30, which is the central zone that's a continuous part of this, which is 30 plus 2A, A being this line that we find on both sides that I'm going to highlight here in orange, there and there. Now, the way that we determine A is we know that A should be equal to 160 minus 10 xi over 20, which should be equal to 8 minus 1/2 xi. How do we know that? We know that because these two are similar triangles, this triangle here and this triangle up here, right? So these two similar triangles should have dimensions that are equivalent to each other. And we know that the top line is A long, and the side for the smaller triangle is 16 minus xi. And so that should be equivalent to 10 meters over 20 meters, which is this part and this part. So we can solve for A by moving 16 over xi to the other side and multiplying it, which gets us the 160 minus 10 xi over 20. And that simplifies down to this value. So we can then simplify this equation here by saying that W is equal to 30 plus 2 times 8 minus 1/2 xi, and then we can further simplify it as such. So we now know that A, which is AI, which is the area of the ith strip, is equal to Wi, the width, which is this part, so Wi is here, multiplied by delta x, which is equivalent to 46 minus xi multiplied by delta x. We're defining delta x to be extremely small, and we're saying that the pressure over the distance delta x does not change at all, and so we don't have to worry about that. And so essentially Pi, so the pressure exerted at I should essentially equal 1,000 kilograms per meter cubed, because this is water, multiplied by the gravitational acceleration constant and xi. Now, as we know, xi is given by these equations up here, and so this can be turned into a summation. F equals the limit of n as n approaches infinity, number of strips, n number of strips, and I is equal to 1, and then you enter your equation, which in this case our equation is here. And remember that this is fairly similar to saying that you have this plot in which you have pressure, there's a force of pressure, and then you have depth. And as depth is increasing, pressure is increasing as well. And so we're essentially just saying we want to find the area underneath this plot from 0 to 16. And to do that, based on the fundamental theorem of calculus, we can turn this into an integral, where we calculate the integral from 0 to 16, and then we plug in our equation. And from there, we can obtain our result. So there you have it. Thank you for joining us. Have a good day.